This example is about accuracy and precision in a set of measurements. Taking a large number of measurements of a physics quantity in an experiment will approximate a statistical normal distribution, where we'll generate some mean or average value. The mean value serves as the best estimate of the true value. Now, most of our measurements will be near the mean value that we calculate. That's just part of a normal distribution. Statistically, though, it could happen that a given measurement ends up very far from our mean, perhaps because of a mistake of some kind. So the term precision is used to describe how spread out our measurements are from the mean and how reproducible the measurements are. Accuracy, on the other hand, is a term used to describe how close the mean value of the measurements is to the true value. Sometimes our mean differs from the true value because we just don't repeat an experiment enough times. Sometimes it's because there's inherent error in the measurement devices themselves, the processes we're using, or human error perhaps. Target practice is an analogy to making measurements. Assume that the center of the bullseye represents the true value of the quantity. Now for A and B, say which shooter was more accurate and which shooter was more precise. Then draw results for C and D yourself. So in order to evaluate these correctly, we should try to find a center or average middle of the markings. Now these 4 dots here would average out to the center. That means that the person who shot at this target did have a sense of where the center of the bullseye was. And for that reason, they are accurate. It means that they know what the true value of the quantity should be, but they weren't always able to reproduce it perfectly. There was quite a bit of spread to the data, to the measurements that were made. Now in this particular example, the center or average of the dots would be not in the middle of the bullseye, which means that this shooter is not accurate. But what they are is they are precise. Because their shots were reproducible, they kept hitting the same spot over and over again reliably. It just happened to not be the correct location. So they weren't accurate. Okay, now let's draw some target practice where the shooter is both accurate and precise. We want the grouping of shots to be in the bullseye, so they know what the true value of the quantity is supposed to be, and they're hitting it every time. That's accurate and precise. Now, not accurate and not precise would mean that they're not reproducing their shots very well, so they should be scattered. And not only that, but the center of mass of them, like the average location of them, should be off-center. That would be not accurate, not precise. All right, we want to keep these ideas in mind for when we draw a normal bell curve to represent repeated measurements being taken. Let's assume that your vehicle is traveling under the speed limit of 65 miles an hour at a true speed of exactly 60 miles an hour. Now let's say that police officers using radar guns are going to measure your speed. So they have an instrument. And this is a fictional example, but let's say several local officers are using identical radar gun models which are very accurate but aren't precise. And then let's say on the other hand that some state troopers are using identical models which are precise but aren't accurate. We want to mark your true speed with a vertical dashed line on the graphs below just so that we know where you're at. So let's go ahead and mark that 60 mile an hour true speed here. And let's do it on both graphs. Okay, now we want to use a normal curve to represent the officer's probability density for measuring your speed. What this means is they're going to make multiple measurements of your speed. Some of those measurements will fall above the mean and some will fall below the mean into a nice bell curve shape, where the majority of the measurements they make fall around that average mean value. Now, when we make a bell curve for measurements that are accurate but not precise, you want to think about what features do we want to see in the bell curve. For example, how wide should the curve be? Should the values be really spread out or should they be concentrated? And also, should the mean of the bell curve be close to the true speed or should it be different from the true speed? We want to think about that for both of these cases. Go ahead and draw for yourself what you think the bell curves should look like for these cases. So if a large number of readings are made where the instrument is accurate but not precise, we actually want a wide bell curve. But we want the peak of the curve to truly be at the true speed. So that way the instrument has a sense of what the true value really is. They know that it's 60. The problem is, though, that the readings are all over the place. Some are too high, some are too low. It's not precise. Now when we do a bell curve for precise but not accurate, we want a narrow curve. And the area under the curve has to be the same in both cases. You have to account for 100% of the readings, and the area under the curve represents the percentages of the readings. So we want a really tall and narrow curve, but we don't want the peak of it to be near the true speed. That's the difference between the two cases. So here, the mean of their readings is different from the true value of the speed of the car. Here, the mean of the readings is the same as the true value of the car's speed. So this is accurate but not precise, and this one is not accurate and precise.